Okay, so far we've looked at SHM, we've derived this result, okay, in terms of the velocity. All right, and remember now, A stands for the amplitude, okay, so the distance essentially that the particle travels from its mean, okay, central point here. So it travels the distance of A, that's its amplitude, to the extreme point here. And the same then with symmetry A that way as well. Now x is measuring its displacement from the mean point, yeah? And we might want to know where it is at a particular point, or how far it's travelled. For that we need an expression for displacement as well, okay? Now we can get that from this derivation here. So we'll rewrite it like this. So if you remember, you just square root both sides, okay? And you get this. We take a positive root, okay? Which will then help us with coming to our solution for displacement, okay? So what I'm going to do now is, because I want an expression for displacement, I'm going to remember what V can be written as in terms of displacement. So if you remember, V is dx by dt, yeah? Velocity is how displacement changes with respect to time. Okay, so it can be written as dx dt. And the whole reason for me doing that is because I can substitute it in there then. I've already got an x here. And then I can solve, like what I'll have then is a differential equation. I can solve it to be able to work out what x is equal to. So substitute it in, dx dt is equal to omega square root a squared minus x squared. Okay, and then I'm going to separate the variables. So remember then, get the x's on one side and the t's on the other. So I need to take all this root over, don't I? I can leave the constant omega there, and this timesing by this, leave that there, but take this over, and of course you take it over and you'll divide. So it'll be 1 over square root of a squared minus x squared. Okay, when you separate the variables, then you put the integrals in, so you have the dx on this side, and then you've got the omega dt then on this side, keep the constant there. So we're going to integrate, and you might recognize then this integral. Okay, this is a standard integral in the integration page in the formula booklet on page 7, and this becomes that result there. So you don't need to remember it, just turn to page 7 and it's there. Okay, and then integrate this side. Well, it's a constant with respect to t, so omega t, and then don't forget then you've got your constant of integration plus c, so we've got that there. Okay, now we need to consider two situations to work out c. Okay, so if I put a star here, let's consider the first situation. So let's consider if the particle, okay, is at O when t is 0. So let's consider the situation where the particle is at the mean point, okay, the center of oscillation at the beginning, at t is 0. Okay, so those are our initial conditions. So that's where we are at the beginning, yeah? Okay, it isn't always the case. Sometimes we here, sometimes we here, right? But let's just consider the case where we're at the mean point, okay? Well, so if it's at O when t is 0, then x will be 0 as well, won't it? When t is 0. X will be 0 because that's where we are, and remember x is measured from here. So to sub it in, sine to the minus 1 of 0 over a is equal to omega times 0 for t plus c, and of course sine to the minus 1, well this is just 0, so because 0 over a is 0, and that equals to c, and we know that's equal to 0. Okay, check on your calculator if you don't believe me. So that means c will equal 0 there. So we have sine to the minus 1 of x over a, if I now sub this into star up here, will equal to omega t and plus then c, well c is 0, so that's it. And what I can do then to get x, think about it, I want to get x on its own, so I'll take that sine to the minus 1 over, okay, because you do it over, you do the opposite, the inverse, so you take it over, that just becomes sine of omega t on that side. And we're left with x over a here, yeah? Okay, and you shift that over there, so you're doing the opposite of the inverse. So you just got sine there. And then to take that a up, so So you've got x equals a sine omega t. And that is our general result, okay, for displacement, okay? But it's important that this will only work for the fact that when t equals 0, x is equal to 0, i.e. initial position is at the mean point, okay? Well, let's suppose it's not at the mean point. Let's suppose it's at the extreme there. So if you think about it, if it was there, or here, x would equal a, wouldn't it? So we could say, if at a or b, i.e. the extreme point, then x would equal a at the start when t equals 0. So let's consider the initial condition so that it's at the extreme point. So x is equal to a when t is equal to 0. So we've got in star, okay, sine to the minus 1 of a over a equals to omega t is 0 plus c. Okay, so x is a, t is 0. Now that becomes 1, isn't it? Okay, that's 0, c. And if you work that out on your calculator, got to be in radian mode, remember, it comes out to be pi over 2. Okay, so therefore, sub back into star, you'll have sine to the minus 1 of x over a is equal to omega t plus pi over 2. Okay, so just like we did before then, take that sine to the minus 1 over, do the opposite, so it'll be the sine of omega t plus pi over 2, and then take the a up. And what's good about this is, okay, that sine omega t plus pi over 2 is a shift of the sine graph, okay, to the left by pi over 2. It's a transformation of the sine to the left by pi over 2 by 90 degrees, which actually is the same then as the cos graph. So there is the general result there, okay? That's the general result for when t equals 0, okay? X is equal to a. In other words, initial position is at the extreme point, okay? So you've got to work out from the question which one you're going to use. Is it this one, or is it going to be the one we saw before? Okay, this one here.